For thousands of years, humanity's progress has been forged in fire. From the first iron smelted in primitive furnaces to the vast steel mills that shape the modern world, our civilizations have been built, literally, on metal. But beneath the roar of blast furnaces and the glow of molten iron lies a truth that's becoming impossible to ignore. The way we produce metal is one of the most carbon-intensive industrial processes on Earth. Every ton of steel, every beam, every car frame, every skyscraper skeleton, carries a hidden cost: tons of CO2 released into the atmosphere. As the global demand for steel continues to grow, the question becomes urgent: how can we forge the future without burning the planet? The answer may come from the lightest element in the universe: hydrogen. Hydrogen metallurgy represents a profound transformation in how we make metal. It's not a distant fantasy, it's an industrial revolution already underway. To understand why it's so important, we need to step back and look at how conventional metallurgy works. Today, most steel production relies on what's called the blast furnace basic oxygen furnace process. In this method, iron ore, primarily iron oxide, is combined with coke, a carbon-rich material derived from coal, and heated to over 1,500 degrees Celsius. The carbon in the coke reacts with the oxygen in the iron oxide, reducing it to pure iron and forming carbon dioxide as a byproduct. This reaction is central to traditional steelmaking, but it's also the source of the industry's massive carbon emissions. Globally, steelmaking accounts for nearly 8% of total carbon dioxide emissions. The brilliance of hydrogen metallurgy lies in replacing that carbon with hydrogen as the reducing agent. Instead of carbon reacting with oxygen to produce carbon dioxide, hydrogen reacts with oxygen to produce hydrogen oxide, water vapor. The underlying chemistry is almost elegantly simple. In the blast furnace, iron oxide, iron 3 oxide, reacts with carbon monoxide, CO, to yield iron, Fe, and carbon dioxide. But if you replace CO with H2, you get iron and water instead. The equation changes the entire environmental footprint of the process. What once filled the atmosphere with greenhouse gas now produces steam. This process is known as direct reduction of iron, or DRI. Traditionally, DRI uses natural gas as the reducing agent, producing what's called sponge iron, which is later melted in electric arc furnaces to make steel. But hydrogen direct reduction, HDRI, is a cleaner evolution of that same concept. The goal is to feed pure hydrogen into the reduction process, achieving zero carbon emissions from the reaction itself. In practice, this requires careful control of temperature, gas flow, and reaction kinetics, but the payoff is enormous: carbon-free steel production powered by renewable hydrogen. The significance of hydrogen metallurgy extends beyond simple chemistry; it redefines industrial ecosystems. For hydrogen-based steelmaking to be truly green, the hydrogen itself must be produced without fossil fuels. That means coupling the steel industry with renewable energy sources through water electrolysis, splitting hydrogen oxide into hydrogen and oxygen using electricity generated from wind, solar, or hydropower. This creates a closed clean cycle. Water becomes hydrogen, hydrogen reduces iron ore into metal, and the process releases water vapor that can condense and return to the environment. It's circular, elegant, and scalable. The world's first real proof of concept for this technology is already operating in northern Sweden, where a consortium known as HYBRIT, Hydrogen Breakthrough Iron-Making Technology, has been running pilot plants since 2020. Developed by SSAB, LKAB, and Vattenfall, HYBRIT's goal is to completely replace coking coal with hydrogen in the steelmaking process. Their early results are astonishing. In 2021, they produced the world's first batch of hydrogen-reduced steel, which Volvo quickly used to manufacture prototype vehicle parts. It wasn't a lab demo, it was an industrial-scale validation of carbon-free steel. But achieving this at global scale is not without challenges. For one, the production of green hydrogen requires vast amounts of renewable electricity. To replace all the coal used in global steelmaking with hydrogen would require hundreds of gigawatts of new renewable power capacity, comparable to building entire continents' worth of solar and wind farms. Moreover, hydrogen is difficult to store and transport. It's the smallest molecule known, prone to leakage, and requires either high-pressure tanks, cryogenic cooling, or chemical carriers like ammonia to move it efficiently. Overcoming these logistical challenges will define the pace at which hydrogen metallurgy scales worldwide. Another technical hurdle lies in adapting existing steel plants. Blast furnaces are built for carbon-based reduction. Retrofitting them for hydrogen operation is neither simple nor cheap. That's why new dry-based plants are being designed from scratch, optimized for hydrogen flow, gas recycling, and electric arc furnace integration. Many of these plants also plan to be hybrid systems, capable of using natural gas initially, then gradually transitioning to pure hydrogen as supply becomes available. This transitional flexibility could be critical in bridging the gap between today's fossil infrastructure and tomorrow's hydrogen economy. Still, the momentum is undeniable. Companies in Germany, Japan, and China are developing pilot programs similar to HYBRIT, and some of the largest steel producers on Earth, like ArcelorMittal and Nippon Steel, are investing billions in hydrogen technologies. Even nations whose economies have long relied on coal-based steel production are beginning to see hydrogen not as competition, but as evolution. In Australia, for instance, projects are underway to combine iron ore mining with local green hydrogen generation, turning the country into a supplier of green iron, a partially reduced, carbon-free product that can be exported for further processing abroad. To appreciate the full impact of hydrogen metallurgy, it helps to think of steel not just as a material, but as a foundation of civilization. Every highway bridge, every rail system, every skyscraper, every wind turbine and solar farm, all of them rely on steel. If we can decarbonize steel, we decarbonize the skeleton of modern life. And hydrogen metallurgy could do for the 21st century what the Bessemer process did for the 19th, ignite a new industrial revolution. One of the fascinating scientific aspects of this transition is how hydrogen interacts with metal at the atomic level. While hydrogen is a clean reducer, it also has a dark side known to metallurgists as hydrogen embrittlement, a phenomenon where hydrogen atoms diffuse into the metal lattice and cause cracking or weakening over time. Engineers and researchers are developing advanced alloys and controlled thermal cycles to minimize this effect. By carefully managing temperature, gas composition, and pressure, they can ensure that hydrogen reduces the ore efficiently without compromising the integrity of the metal. These are the kinds of details that will determine whether hydrogen metallurgy becomes the dominant standard or remains a niche solution. Energy efficiency is another key area of innovation. Although hydrogen-based reduction eliminates carbon dioxide, the process itself requires more energy than carbon-based methods, since hydrogen must be produced and heated. This is why coupling hydrogen metallurgy with renewable electricity is crucial. Using fossil-based hydrogen would simply shift the emissions upstream. To avoid this, many projects are exploring co-located renewable generation, building electrolyzers right next to steel plants, allowing direct use of solar and wind energy for hydrogen production. Some advanced concepts even involve integrating thermal energy recovery systems, where waste heat from the steelmaking process is used to power electrolysis or preheat incoming gases, closing the loop even further. What emerges from all of this is not just a cleaner form of steelmaking, but a blueprint for industrial symbiosis. A future hydrogen metallurgy complex might include renewable power generation, large-scale electrolysis facilities, hydrogen storage caverns, dry plants, and electric arc furnaces, all operating as an interconnected ecosystem with minimal waste. The byproducts of one process feed the inputs of another. The water released from hydrogen reduction could be condensed and reused in the electrolyzers. The oxygen produced during electrolysis could support combustion or oxidation processes elsewhere in the facility. It's a vision of industry as an organism, not a machine, self-sustaining, adaptive, and efficient. Hydrogen metallurgy also has geopolitical implications. Today's steel industry depends heavily on coal, much of it imported from specific regions. Transitioning to hydrogen could redistribute global power balances, with nations rich in renewable potential, like those with vast desert or coastal areas, becoming major players in the green steel economy. A country with abundant sun and wind could export not just hydrogen, but carbon-free steel products, creating entirely new economic networks based on sustainable energy instead of fossil resources. The ripple effects could reach beyond steel. The same hydrogen technologies can also decarbonize cement, glass, and chemical industries, sectors that have traditionally been considered hard to abate. As hydrogen infrastructure matures, economies of scale will make it cheaper and more accessible, accelerating adoption across multiple industries. The more we produce hydrogen, the cheaper electrolysis becomes. The cheaper hydrogen becomes, the more industries can transition. It's a virtuous cycle of decarbonization. Critics sometimes point to the current cost of hydrogen as a barrier. Indeed, green hydrogen is still several times more expensive than fossil fuels. But cost trajectories in technology tend to follow a familiar pattern, what economists call learning curves. Every doubling of production volume reduces cost through innovation, optimization, and scale. This has already happened with solar panels, batteries, and wind turbines. Hydrogen is following the same path. By the 2030s, many projections suggest green hydrogen could achieve cost parity with natural gas, making hydrogen metallurgy not just clean, but competitive. What makes this transition even more fascinating is how it brings together multiple disciplines: chemistry, materials science, energy policy, and planetary sustainability. Metallurgists who once studied slag chemistry and furnace dynamics are now collaborating with renewable energy engineers and data scientists. Artificial intelligence is being used to model reduction reactions, optimize furnace efficiency, and predict material performance under hydrogen atmospheres. It's a perfect example of how the fourth industrial revolution, driven by digital and green technologies, is merging with the original industrial foundation of metal and fire. From a broader human perspective, hydrogen metallurgy represents something deeply symbolic. The earliest blacksmiths learned to control fire and shape metal. It was an act of mastery over nature that defined civilization. Now, thousands of years later, we're learning to forge again, this time with the universe's most abundant and simplest element. Hydrogen is both ancient and futuristic, both the first element born from the Big Bang and the key to a cleaner industrial age. In a sense, hydrogen metallurgy reconnects us with the fundamental elements of existence: earth, air, water, and fire, combined in harmony rather than conflict. If we imagine a future city built entirely from hydrogen-produced steel, its towers and bridges gleaming under the sun, we're seeing not just architecture, but philosophy. Every beam in that city would be a declaration that progress no longer requires pollution. Every structure would carry the story of innovation, cooperation, and respect for planetary limits. Hydrogen metallurgy is more than a new technology, it's a moral turning point. It asks us to evolve from the extractive mindset of the Industrial Revolution to a regenerative mindset for the future. To keep building, but to build responsibly. To keep forging, but without the smoke. And perhaps most inspiring of all is that this isn't distant science fiction. The first hydrogen steel plants are already operating. The first vehicles made from green steel already exist. The first nations to adopt hydrogen metallurgy are already reshaping their industrial identity. What once seemed impossible, making metal without fire and carbon, is now real. In the decades ahead, when historians look back on the transition to a sustainable civilization, they might point to this era and say, this was when humanity learned to forge cleanly. When we replaced coal with the breath of the universe itself. Hydrogen, the most abundant element, may soon become the most transformative. And the story of hydrogen metallurgy will stand as proof that even the oldest industries can reinvent themselves for the future, turning the very process that built the modern world into one that sustains it. Hey everyone! If you enjoyed this video, make sure to hit that like button, drop a comment to share your thoughts, and subscribe so you don't miss any of our future uploads. Your support helps this channel grow. Thank you for watching.